Okay, why don't we get started? Welcome to the webinar, Human Machine Interface, or HMI, Design to Improve Operator Response to Alarms. My name is Todd Stauffer. I am the Director of Alarm Management at exida. Similar to other webinars in the past, all the attendees will be muted. If you have questions or comments or feedback, please enter that into the questions box and we will take a look at that at the end, try and answer with any extra time we have, or most likely capture all the questions and answer them as part of the follow-up email that comes out. So as I mentioned, my name is Todd Stauffer. I'm the Director of Alarm Management at exida. Been involved with ISA 18.2, which is the alarm management for, or it's just a standard for alarm management in the US, as well as some of the other activities that the ISA committee works on related to alarms, creation of technical reports and other things. If you're not familiar with exida, we were first formed in 1999 with a goal to make the world a safer place, in particular process plants. We got started in the area of functional safety, but then expanded to include cybersecurity and alarm management, which are other key areas that impact the risk of a plant. We do certification of people, processes, and devices. If you've ever worked with a safety instrumented system and needed to design a SIL2 capable function, chances are you were working with equipment that was certified by exida. We also have a program for certification of people to demonstrate competence that exists for functional safety as well as cybersecurity and alarm management. We have a suite of tools for safety instrumented system design and engineering, essentially to walk you through the whole entire functional safety lifecycle. As part of that, we also integrate tools for cybersecurity as well as alarm management, and that would be our SIL alarm rationalization tool. So the purpose or the goal of this webinar is to talk about how to improve operator performance when it comes to responding to alarms. There are lots of different performance shaping factors for operators. We're going to focus solely on the interface, so the human-machine interface. So we won't address workspace ergonomics or things like that, or training and job aids. We're going to focus solely on interface design, which is bringing together the ISA 101 standard and the ISA 18.2 standard. So we will talk about situation awareness during this webinar, talk about what it is, what it means, what it does for the operator. We'll also spend the first part of the discussion talking about human factors, things that we've learned about how humans behave that impact how we might choose to design a human-machine interface. From that comes best practices and guidelines, some coming from the ISA 101 standard. So we'll go through some of those guidelines and best practices related to things like how to use color to enunciate information or to provide information to the operator, the design of process graphic displays, alarm summary lists, and then we'll look at how we can tie those things together, optimizing displays and alarm summary list to create a different way for an operator to be able to respond to alarm floods, truly optimizing the design to give them a fighting chance during the alarm floods. So first, let's talk about the evolution of the control room, what it looks like to the operator from the operator's point of view. In the olden days of panel board control rooms, the operator, like you see here in this picture, could stand and look out and see all of the devices and equipment and instruments that they were responsible for. So it was all there in front of them. Due to the layout of the information staying the same over time, you can also imagine that an operator working with the same equipment for month after month would develop some pretty good pattern recognition of what to expect of the different pieces of equipment, and when the patterns don't match, what that actually means. So they did develop a good situation awareness, a good way to look at the status of things and at a glance be able to tell whether their unit that they're responsible for was working well or was in an upset area. Fast forward to the modern process control system, where operators typically are asked to do even more. They are responsible for more process areas than they were in the past. Each process area has more equipment, more instrumentation, and more process measurements. So there's a lot more data for them to process and a lot less real estate to do it in. You can see in this display, the operator has basically 2 computer screens, 2 monitors to be able to interface with the process and get information on all the hundreds of IO points that they may be responsible for. So in a situation like this, it's very difficult for them to be able to see the status of all of the areas that they are responsible for. And it's also difficult for them to know for sure what's going on. The surveillance of the system and understanding how things work at a glance and their status is much more challenging in that kind of an environment than in the old control room, the panel board control room. So it's difficult for them to get a good feel for what's happening in the process. So what we're going to talk about is the design of the human-machine interface and secondarily the alarm system design, as those are the primary ways that operators get information about how the process is working and how they interface with it. So when that goes wrong and we see operator errors, not necessarily meaning that it's the operator's fault, but that can result in some significant events, including some of the more famous industrial accidents have alarm system and HMI system faults or poor designs as their contributing causes. In fact, the Buncefield explosion in 2005 is an example of both an alarm system and an HMI system failure, if you want to call it that. In that incident, a tank was being filled by an operator, and that the gauge that provided the operator with the measurement on the level in the tank, and which was used to generate an alarm to tell them when to stop filling the tank, that instrument failed, and it failed at a intermediate value. So it didn't fail high and didn't fail low, and no alarm was generated. But there was supposed to be a second safety alarm that would go off when the level got real high, but unfortunately that didn't work. So we had 2 alarms that failed to occur, an HMI that didn't provide indication or notification to the operator that they were about to overfill their tank or that something was wrong. And when the tank overfilled, it released hydrocarbons, and there was a gigantic explosion, and billions of pounds worth, or 1.5 billion pounds of damage was caused by this explosion. So the root causes, when the investigation was done, some of the contributing causes certainly were the failure of the alarms, but the design of the HMI did a poor job at providing the operator with situation awareness. So just because the alarm didn't occur, there should have been some indication within the HMI or some other way to tell that there was a problem. to take the place of the alarm that didn't occur. So we want to try to eliminate human error or minimize it. And as we've progressed and operators have been responsible for more process areas and equipment, that's led to greater automation, and it's actually made the problem more challenging as we go forward than it has in the past. So the challenge of increased automation and human error due to complexity, increased cognitive load, and reduced situation awareness, all that stuff mixed together can end up with an incident. So we want to talk about how to prevent that and how to make the HMI optimum for the operator, especially during upset situations. And we'll leverage two different standards that have been created. The first one is ISA-101, which is on human-machine interfaces. So that defines some of the best practices about documentation and design for how to create the HMI to be effective for a process operator. We'll also, to a lesser degree, reference the ISA 18.2 standard on alarm management. So what we're looking at is those two standards to guide us to create an operator interface that will optimize the operator's response to alarms. So let's see how that happens. And what we will start with is a discussion of human factors. So what do we need to know about how us humans act and behave? What do we need to know first before we launch into creating process graphic displays? What lessons do we need, and what things do we need to understand before we launch into that? So we'll start with a discussion of situation awareness. What is it? It's essentially the ability for the operator to receive external cues in the control room. In this case, we're talking about things like alarms or horns, or noticing changes on the HMI, or trending information on the HMI and being able to project out then what that information means. So what's happening in the plant? What's happening in the process? The information that I'm getting now, what does that mean is going to occur a half an hour from now? So near term, and also projecting it out longer term, so that they can really have a grasp for what is happening and where the process is going. Now, as part of that, they're using their mental model, which is essentially their way of understanding how the process works. They're using their mental model to project out what's going to happen in the future based on the cues that they are receiving today or right now. So that's where the mental model comes into play. And what's important about this? What do we need to know? What takeaway do we need for effective HMI design? Well, realizing and understanding that there is a mental model, there's some way that the operator understands and thinks that the process works and interacts and interrelates. So wouldn't it make sense then, when we're thinking about how to lay out graphic screens and design the HMI, to potentially try and understand the operator's mental model of the process and maybe design the HMI to match with that? Might make it easier for the operator to relate to. As part of the operator responding appropriately, let's look at the series of steps that they go through and understand where human factors comes into play. So the first step in the operator's successful either response to an alarm or response to an abnormal situation is that they need to detect that the situation exists. They need to realize that something is happening. And if the interface that they're working with, the two computer screens, for example, if that's not designed well, then they might not immediately realize that there's a problem, or they might not see an alarm if there's a whole bunch of other alarms, or if there's lots of flashy colors on the process graphics, it might make it so that the operator doesn't see that new situation or the evolving situation, so they miss it. Second step in the process is to diagnose what is happening. So this is where they really put their mental model to use. So they've got the input, the information, the cues coming from the HMI, and they need to make sense of it all. Understand what is happening, what's about to happen, what could happen, so that they know what the appropriate corrective action would be to take. So a poor HMI design or poor alarm system performance can make it more difficult for the operator to diagnose, but more importantly, they can diagnose it incorrectly, given misleading information or a misunderstanding of what is happening. So their mental model could be wrong, or they could be interpreting incorrectly. So good HMI design is important to help get the operator through this diagnosis step. And the last step in the sequence is for them to take the corrective action to respond, typically through the HMI. And what we found in analyzing a bunch of overfill situations or tank overflow examples, that most of the time, 90% of the time, the step that led to the problem, the real failure step, was the diagnose step. So that's where the operator is using their mental model to figure out what is happening and what they need to do. So that points out how important it is for us to help address that situation. So we talked about detection being the first step. So if we think about it from a signal detection point of view, what are the potential problems or what could go wrong to make that not work? Well, in general, humans are not great at detecting changes. So just looking at the screen here on the left, the top half versus the bottom half, and trying to notice the differences, there are 10 of them, by the way, is not something that's easy for humans to do. So that's a challenge, and this indicates what would happen if the signal that you're looking for, the event or the presentation of the abnormal situation, is hard to differentiate or distinguish from all the other information present. And that's certainly the case for the examples that we see here. So that is a potential cause of detection failure. It can also be a failure if there's too much information coming at the operator too quickly, that they can't process it enough in a timely fashion. So what does this mean? What do we take away from this? Well, we want to do things to make it easier for the operator to detect the situation that we want them to know about. And the way we do that is typically by reducing the visual or background noise, and we're increasing what's called the salience of the signal itself. So ideally, we would reduce the content on a process graphic of the static content, the stuff that doesn't really impact the operator understanding what's happening and doesn't really impact what they do. If we can eliminate some of that static stuff, that reduces the visual noise. Then also in conjunction with that, we make the indication stand out more. We give it more salience by using color and text and other techniques for making it easy to see. Now, of course, we're not just talking about games here or puzzles and things like that. This is certainly relevant to real process displays, such as this one that we see here, where looking at it, because of the number of lines and the different colors and things that are here, it would be very challenging, or it may be very challenging to detect a state change on here. So given the things that we talked about, this is an example of how that might manifest itself. Another thing we want to be mindful of is what's called blank screen syndrome, or the absence of cues. So not only are people not good at detecting change, but they're also not really very good at inferring something from its absence. So what that means, let's imagine that we had two different ways to display alarm information or status information. In the top, as part of an equipment display, we're showing the indication that there is one alarm active at the time, but we do not show the status of other potential alarms related to that equipment. So that's invisible. So we don't know about it. So one could think, out of sight, out of mind, the operator doesn't need to know. But that's not really true, because the story or the interpretation of the situation for the top display is very different from the bottom display, where you have disclosure of the other alarm conditions that could possibly be present but are not active at the time. And certainly the operator's understanding of the process or their mental model is going to be much stronger and much better reinforced with the information shown on the bottom display, so not truly hidden, than it is from the top. So we want to keep that in mind as we're designing displays to make sure that we're not hiding information that would be useful in contributing to the operator's understanding of the situation. When it comes to getting information, there's really, we could think of it as two different channels to our brain. The first one is a sensory channel. So we're using our senses to see, to smell, to touch, to hear. That is independent from the channel that uses for conscious evaluation and information review. So what this means is, when we first look at a process graphic display, we're trying to understand consciously what the information means. In parallel, we are evaluating the color that's there and starting to react based on what that channel is seeing, our sensory channel. And what can happen then, if we know how the sensory channel works and we want to use it to its optimum, we need to understand what can happen when it works well and what can happen when it's not working well. And the Stroop word color test, shown here on the right, is an example of showing how this sensory channel works. If we read the names of the colors at the top, that causes a conflict in our brain from the cognitive channel and the sensory channel as well. So instead of causing confusion and inconsistency, our takeaway is that there is this second channel for absorbing information, and it happens in the background. And if we use it effectively, it's another way for the operator to get information and understand what's going on. So the best way to use it then is to come up with a color scheme that's consistent. So we use colors for alarms such as red, but we reserve those colors and don't use them for anything else. Then this sensory channel of information, when it sees red, it starts to get your brain activating or getting things moving that there's an abnormal situation present. So we want to make sure that we're using color appropriately to optimize the communication and processing in the sensory channel. Now the other channel is the conscious processing of information, which goes into our short-term memory banks. And studies have found that in terms of short-term memory, humans typically can only hold 7 plus or minus 2 pieces of information. Now the pieces of information can be of different sizes and can be structured differently to optimize what's stored in that memory. So the process of what's called chunking is a way to group information so that more data essentially can be transmitted in one of the chunks, one of the 7 things that we can juggle, and doesn't require multiple individual data chunks or receptors to be able to understand. And a good example of that is how we document and think about telephone numbers. a phone number in the US is 10 digits plus country code. If you just put those all together, it's much harder to remember that number than it is if we break up the phone number in its pattern of country code, area code, 3 numbers, and then 4 numbers. So in that example, when we chunk that information and break it up like that, it's easier for us to remember it. So we need to extend that to process graphic displays, which means we want to group information to create information chunks that operators can assimilate or understand very quickly and very easily. And that impacts their cognitive workload. So how much mental effort do they put in or need to put in to be able to execute a task where they need to think about things? So that's important to know or to think about or to understand, because the way you design the operator interface can drive the need for more or less cognitive energy by the operator. And ideally what you want to do is create the system that gets the information across with the minimum cognitive load. So for example, if the ratio of 2 flows was what was important for the operator to know and to understand, it would be much more efficient to have the HMI calculate the ratios and present that or show that graphically, instead of just showing the individual flow rates and forcing the operator to do the calculation or the representation in their mind to understand what the ratio is. So in the second case, the cognitive workload to understand the ratio would be much higher than it would be if the HMI did that and presented its results automatically. There's also some other biases that we need to understand and think about when we're designing human-machine interface. Cognitive biases are systematic errors that people make in the way that they think or judge situations. So it impacts their decision-making process. We also need to keep in mind confirmation bias, which is the tendency to interpret new information in a way that basically just confirms your existing beliefs. And this can be a problem really for experts. The more expert you are, the more likely you are to suffer from confirmation bias, because you are so knowledgeable. Once you make up your mind about what you think is happening, sometimes new information, instead of causing you to rethink your understanding, what you do is you reformulate it in a way that it corroborates what your initial assessment was. So knowing that these things can happen, we want to take that into account when we design the human-machine interface and try and minimize or prevent those biases. We also need to know or understand how people make important decisions. Classical decision-making theory, or the way that we think people make decisions all the time, involves first defining the problem, coming up with what the alternatives would be, evaluating each alternative, kind of ranking them in your own mind, doing pros and cons, and determining which one has the greatest benefit, and that's the one that gets selected. But what we found was, in real life, that is not the way experts make decisions in short periods of time. Under emergency or critical scenarios, they do something very different. They develop a idea on what is happening based on things that have happened in the past. So they look for patterns and try to use that within their mental model to postulate what is happening. And based on their previous experience, they would know what they should do. So the idea is they're taking the visual cues and trying to match them to something that they've seen before, or adjusted from something that they've seen before, but something that's close. And they use that to then drive their understanding and their action on what to do in response. Nuisance alarms are a common problem in alarm management, and rather we're not going to talk about the way to solve it from an alarm management point of view, but there's a couple parts of this that are relevant and important. So nuisance alarms are alarms that come in that doesn't matter whether the operator responds or ignores them or whatever, nothing happens. The alarm doesn't go away, no consequence occurs, so they're really not alarms. But it creates the thinking within the operator that they can ignore alarms. So what this means, or what we need to take into account here, is that there's a need for operators to be able to corroborate or validate alarms. So if there's an alarm that comes in that they think is a nuisance alarm, or they think may not be valuable because they're used to seeing nuisance alarms, if we can present other information within the HMI on the same process graphic screen that would corroborate whether that alarm is real or not, that's the best way to go. So we want to provide corroborating information to validate the scenario. Example of where some of these situation awareness topics come to play is this example from a running refinery in Canada in January, where they were filling a treated water tank. There was a failure in the level controller. It resulted in a high alarm being generated. So the operator responded by reducing the flow. A couple minutes later, another alarm came, but this time it was actually the low alarm from the redundant transmitter. So the mental model of the operator, if they truly understood what they were seeing, would say something is wrong here. It's impossible to have both a high and a low alarm at the same time for redundant measurements. But instead, the operator experienced some confirmation bias. When the low alarm came in, they actually thought it was a high alarm, and they reduced the output further, thinking that the level was getting too high. They didn't take any additional action for 8 hours, and they didn't realize what had actually happened, essentially draining the tank, until the outlet pump started to cavitate. And by the time they tried to fix it, they had shut down the boilers to working refinery in Canada in January. Not a good situation. So when we investigated some of the modes of what happened, the failure modes, one of the things that jumps out at you was, hey, there was this redundant piece of information within the HMI. Why didn't the operator look at that redundant transmitter as part of their diagnosis of the problem, as part of their validation of his mental model? And they should have. That was a failure on the operator's part, but it also shows why that corroborating information is important. Now, they were conditioned to not value alarms because they had a lot of nuisance alarms already present, and they also had issues distinguishing that second alarm that came in. They mistook it as a high alarm because the way the alarm summary was created, most all of the information was the same. The only thing that was different was 2 letters in the alarm type field, so PV high versus PV low. So that's what, again, led them to misinterpret what that alarm meant. Confirmation bias. improper mental model, errant mental model, and then they took the wrong corrective action and ended up with an incident. So now we're going to switch gears and start to talk about what are the HMI design guidelines and best practices based on those human factors topics. So we want to design the HMI to be effective during abnormal situations when you have lots of alarms, during a normal operation when you're getting singular alarms, perhaps one at a time, maybe don't even have alarms present for portions of the time, and for optimizing the process as well. Now, the guidelines for design of displays, there's two elements to that, or two facets. First, we'll talk about the content, what should be included or what shouldn't be, and then we'll talk about the formatting or the presentation. Now, between those two, content is really more important, because if you don't have the right content on the process graphic, it doesn't matter what level of special formatting or presentation you do, it's going to be hard for the operator to understand it. So, but we're going to focus on both of those things. One of the most challenging parts of HMI display design is understanding what information should be included and what should be left out. So the idea that there's a lot of detailed information about how the process works or how the equipment is designed or looks that could be put on this display doesn't necessarily make it so that you should put it on the display. We want to kind of make sure that we're only adding what's necessary information to help the operator make decisions and take action. Now, the ISA-101 standard defines, as we mentioned earlier, some guidelines and best practices. One of the key tenets is providing information in a hierarchical fashion. So it's recommended to use 4 different levels of hierarchy. The highest level, level 1, being an overview of the operator's span of control. Second level being more detailed graphics for a subsection or a sub area, which would be where they would probably spend most of their time interacting with the process. And then a level 3 and level 4, which provides more detail. Now, we'll notice that this is laid out in a hierarchical fashion, which is consistent with the idea of chunking and putting information into small packages and expanding as you go down further in a hierarchy. So it's very consistent with how we optimize the presentation of information for short-term memory purposes. It also represents the way our brain is structured for organization and storing of information. So the level 1 displays are supposed to represent the key information that the operator needs to know from their span of control. So it should answer the question, do I have any problems within my span of control? So what it's going to show is status of key process equipment, maybe selected important alarms, KPIs, whatever gives the operator that high-level understanding of the status of the process. Been in scenarios where we see people creating a lot of different overview displays and kind of tying them together. But the idea is we really just want one display that the operator can look at, similar to the panel board control room concept. One thing that they can look at to know whether they have a problem or not, and what area of the plant is the problem. Then they would go to the level 2 displays for the appropriate area of the plant, and that's where they really figure out what's going on and take most of their corrective actions. So 80% of the actions they take would typically come from this level 2 graphics. It's also going to show more of the alarm status and have links to additional more detailed information and alarms, diving down to level 3 and level 4, which are more diagnostic displays. So we lay out process graphics in a hierarchical fashion. Now let's talk about the display of what goes into the HMI graphics, the colors and symbols that are used. And if we look at these two different renditions of a process graphic, essentially showing the same thing but portraying the information in two different ways. The one on the left, our eyes are drawn to the blinking agitator and heat exchanger. And the attention is drawn incorrectly, actually, because those are not alarms. If we see on the right-hand side, the only thing that is blinking or represented in a different color is the alarms in the abnormal situation. Those same alarms exist on the left-hand side, but you can see they're much more difficult to see. And there's various reasons why it's difficult to see. Relating back to the human factors things we talked about, there's more visual noise in the one on the left. We see a lot more detail in some of the static components. For example, these three things that might be added to the reactor. There's also misplaced salience, so that's your eyes are drawn to the blinking green, even though that's not really what you should be focusing on because it's not the abnormal situation. And it's a poor use of color, so it's not correctly using our sensory communication channel. And why do I say that? Well, the typical colors used for alarms are yellow and red. And if we look at this graphic here on the left, we can see that yellow and red are used for process piping. So there's nothing abnormal about those. It's just the way it was chosen to represent what was going on. So again, what happens in our sensory communication channel? We see yellow and red, which are the colors of abnormal situations. So our brain starts to spin up that something is wrong, but it's being tricked because it's being triggered by things that don't relate to abnormal situations. So that's a poor design. So the other takeaway from this slide is how we decide how to display different types of information, and its importance depends on what it's used for, and its visibility then relates to its importance. So if it's background information, it's low visibility. If it's an abnormal condition, we want those to jump off the screen. So focusing more on color again, then we can't just focus on color actually for presentation of status changes and alarms and events, because 8 to 12% of the male population is colorblind. So that means if the only way to tell that there was an alarm present was by a color change, then there would be a good portion of control room operators that might never notice it or might not understand what it really means. So the way to get around that is to use more than just color, to have redundant encoding, if you want to call it that. So we use text, we use symbols, we use blinking, we use patterns. And you can see here we're going to represent the status of an alarm through blinking of a border. We have a colored symbol with exclamation points in it. And that symbol is different in color and pattern depending upon the priority of the alarm and its status. So even if you're a colorblind operator, you can still distinguish between an urgent priority alarm and a high priority alarm, for example, because of the way color and redundant encoding is being used. Now, one of the other takeaways related to the use of color and blinking is when you implement blinking, you don't want to make the text or the important information that you need, you don't want to make that be what's blinking. So we wouldn't want the process variable value to blink as part of an alarm. We want something around that to blink, because if the process variable starts to blink, then during half of the visual cycle, we won't be able to read what it says. So we wouldn't want to use that as the way blinking gets implemented. So in terms of summarizing some of the key rules for the use of color in HMI design, we ideally want to reserve alarm colors, not use them for anything else. That makes the sensory communication channel very clear in its interpretation of what those colors mean. We want to use conspicuous colors. We want the color coding of alarms to reflect the priority and the state of the alarm. Choose our background colors wisely. Minimize the number of different colors used so the operator can understand what the different colors mean, and use color consistently. And this is important. I've seen examples where it's not been done this way. So one scenario I have seen is alarms on process graphic displays all use the color red to get the operator's attention, no matter what the priority of the alarm is. But the alarms, when they show up in the alarm summary display, are red, yellow, and purple, depending upon the priority. So that means something that was red on a process graphic display might be yellow on the alarm summary list. Not a good practice. Now let's talk about how to display information and the use of quantitative versus qualitative formatting. So which method is better here? The one on the left, which makes it very obvious what the temperatures are of the different levels in this distillation column, or the one on the right where we don't actually even see the values? Well, the answer is it really depends on what the operator needs to do with the information. So if they are trying to understand how well the column is working and whether it's doing what it's supposed to, then the display on the right provides a much higher level of understanding than the one on the left. The one on the right shows us the variation in temperature change from one level to another. It also shows that temperature in relation to the normal operating range for that level of the column. And it shows it all qualitatively in an abstract fashion that one can look at and understand. So your understanding of the process from the display here on the right is probably more rich and rigorous than the one on the left. However, if the operator needs to know the actual value of the temperature for one of these levels in the column to perform a calculation or to do something, then you do need the analog measurement. So you really adjust the formatting depending upon what the information is going to be used for. In general, though, we want to go toward a more abstract display like this because it allows a richer mental model to be developed and a better situation awareness. The operator can see patterns and understand those patterns much easier than with the display on the left. Speaking of patterns, that's really one of the things we want to strive for in the design of the HMI graphics. We want the operators to be able to see and form their own patterns based on the information so that they can use that to quickly assess what's happening and to validate their mental models. So the display of information going from just pure analog numbers to display of analog numbers in combination with bar graphs of the range, or to also to include alarm limits, is sort of a more optimum approach than just analog values. And down here on the bottom, we show selected key process variables normalized across their range and in relation to what their normal operating range is, including alarm limits and the set point of the process variable. So a lot more understanding of patterns, or patterns can be developed with the representation on the bottom than a couple of displays of analog numbers. Another factor to keep in mind is determining how much realism we put into the design of the graphics. In the more modern HMI packages, you can make your graphic displays look like the real thing. So most people would think that that's good, that those are more attractive for sure, and that must be the best way to portray the information. But your brain is not a projection screen, it's really an information processor, and it works better when you present the information in a more abstract and representative way than to worry about trying to get it to look like the real thing. There was some testing that was done on operator performance given process graphics that looked real, like the real thing, and those that used a more abstract concept for presentation of information. And of course, the ones that are more real, people like better, but it turned out that they performed significantly better on the other process graphics. So the graphics that were designed accentuating abstraction and representation of information were more effective than the ones that were designed to be as real as possible. So if we apply some of these lessons to the Buncefield incident, we don't really know what the HMI looked like, but essentially what happened was level measurement failed, not high or not low, and then the alarm that we were expecting to occur when it reached high level did not, and the tank ended up overflowing. But it begs the question, couldn't the HMI have presented information to let the operator realize that there was a problem, even though they didn't get an alarm? And for sure, you would think that there would be. So again, we lost the validity of the process measurement. But if we designed our HMI in the ways that we've been talking, with lots of corroborating information, such as the real-time trend, flow measurements, talking about what's going into the tank, then one would hope that from this, the operator would notice that there was a discrepancy between what the level gauge was showing and what should have been happening. So their mental model would have been able to pick up that, why am I adding to my tank, but yet my level is flat? That would again violate the mental model and indicate that something is wrong, and they would be able to investigate and hopefully would have been able to realize that their tank was almost full or was full before they actually overflowed it and caused the incident. So it also shows how important it is to put the confirming measurements for alarms, because operators need to be able to validate that an alarm is real and that the hazardous situation that it's talking about or it's dealing with is a situation that they need to respond to. So in terms of summarizing some display recommendations, we don't want to just redraw PNIDs. We want to eliminate irrelevant detail, minimize noise, the visual noise, by focusing on just the stuff that will help the operator respond or understand what's going on. So focus on the dynamic data, not the static information. Arrange information on the displays so that operators can develop their own patterns to understand how and why things work the way they do. Choose the appropriate format for display of data based on what the operator needs to do with it. Use abstraction and chunking to condense information and present it in the most optimum way. And to be careful about using invisibility to hide information that the operator needs to know to contribute to their understanding of what's happening. The last thing we want to talk about is alarm summary displays, and then we're going to look at combining all this together in response to alarm floods. So good alarm summary displays provide quick and easy access to the process graphic that the alarm occurs on. In many cases, or most cases, there's a dedicated display in the control room to show the summary of all the alarms in the plant or all the alarms from the operator's span of control. Now, these alarm summary displays can often be configured to present the alarms in different order, certainly chronologically being the most common, but you could also do it by acknowledgement status in combination with priority. So now let's see how we combine some of the things that we've talked about to help the operators respond more effectively during an alarm flood. So the first thing we want to do is have good level 1 overview graphics. So here's an example from a refinery where we have the key information, key equipment represented all in one place, the status of all that key information, and we have the status of alarms aggregated up to the top, meaning if there is an alarm present in that process area, then it's indicated on this little summary display. So we would see whether there's alarms present. We would also be able to tell what priority those alarms are in. So the whole idea is to have this singular overview that the operator can then see when the alarm flood starts to come in, which process area is the one that has the problem. And that's what we want to get out of this level 1 overview. Because if we're staring at just the alarm summary display during an alarm flood, it's not going to be very useful. It's not going to be very effective if it's designed in a typical fashion. And that's because as new alarms come in, the older alarms are scrolling right off the page or actually moving down the page. So if you're trying to read and understand and diagnose and compare to your mental model, and the information is moving all over the page, that's going to make it pretty difficult for you to do much with that. So it can also make it difficult to understand the relationship between alarms, understand the causal patterns. So what's a better approach, based on some testing done by the Center for Operator Performance, they found that during alarm floods, operators can do better, actually do better than what's defined in the ISA 18.2 standard in terms of number of alarms to respond to. They can do better than that metric if the summary display is created in a way that keeps the highest priority alarms at the top always. And what does this mean? So that effectively would mean that as new alarms are coming in, it's not pushing the high priority alarms down and off the page. They all stay at the top, and it makes it much easier for the operator to focus on those high priority alarms during the upset as part of their response, which is essentially what you would want them to do. That's the whole purpose of priority. If you have multiple alarms that occur, which ones do I need to respond to first? It's the high priority alarms. So now let's look at how we could use that information and change the way operators respond during an alarm flood. So the typical practice would be you're staring at your alarm summary for the entire plant, and all of a sudden the upset occurs and the flood of alarms start to come in. The alarms are scrolling past, the horns going off. The operators are acknowledging alarms, silencing the horn to try and figure out what's going on. But if they're just staring at that alarm summary display for the whole plant, it's going to be pretty challenging to respond appropriately and respond effectively. So a better way is to start with the overview, which is again going to identify which process area is the one that has the problem, which is the one that I need to focus on now, realizing that the other ones I need to set aside to deal with this upset. So the overview identifies the process area that you're having the problem with, and it takes you down then to a alarm summary display. But in this case, it's not for the entire plant, it's just for that process area that is the one that has the problem. So it's pre-filtered to show essentially just the relevant alarms in this case. So that makes it much easier then for the operator to get their hands around what's happening and recognize the patterns of what the different individual alarms mean based on when they occurred. So from this filtered alarm summary display, the operator can get a feel for what's happening, then go to the process graphic to address, and then come back and acknowledge all the alarms. So this has been found to be a more effective way of responding to alarms during alarm floods, leveraging some of the techniques that we just talked about. Another finding in this research by the ASM was that during alarm floods, it's actually more effective to present alarm information in a temporal fashion, such as what you see here. This actually enables the pattern recognition that operators need or key off of much easier, makes it much easier for them to understand what's happening. So instead of a scrolling list of alarms, we see a stack of alarms that have occurred in a certain slice of time, and we can see how they relate to each other from a time point of view. We can also see how they relate to other actions that were taken by the operator or other process measurements to help us understand the cause and effect. So during an alarm flood, the traditional alarm summary displays are not very effective. Filtering them can make them better, but an even more novel approach is to use this kind of alarm timeline display that again is filtered on the relevant process area to make it easy for the operator to understand what's going on. So we're reaching the end here. So wrapping up and summarizing some of the key things that we talked about, we discussed important human factors understanding or knowledge, things that we want to know about before we start launching into developing HMI displays. So we want to keep that human factors information in mind as we create new projects, before new projects, and during development of graphics. We also talked about the importance of situation awareness and mental models, what they are, when they get used, how they help the operator, how the operators use them to maximize situation awareness. We want to reserve alarm colors, not use them for anything else. We want abnormal situations to have maximum salience and clearly jump off the page. We also talked about providing confirming information on process graphics to help the operator truly understand what's going on and to allow them to validate an alarm that comes in. We talked about using abstraction and patterns to help represent the process and provide information in a different way that supports pattern recognition amongst the operators. We want to choose our colors wisely, make sure that we're presenting alarms using more modes than just color, so text and symbols. We reviewed how alarm summary displays work, how they're designed, how they can be optimized for use during an alarm flood, and how they may not work very well during an alarm flood. And we talked about some of the requirements or guidelines and suggestions of the ISA-101 standard related to laying out process graphics in a hierarchical fashion. So on that note, we are drawing to a close. These are some of the references that were used in the development of this webinar. And at this point, I'll turn it over to questions to see whether there are any. I know we are a little bit past time. So I think what we will do is capture these questions or give you all a couple of minutes to enter any additional questions that you might have, and then we will answer them as part of the follow-up. So at this point, I'll say thank you for joining then. I hope you enjoyed this webinar. And if you're interested in learning more about alarm management, there are many previous webinars on the Exida website and on our YouTube channel, as well as lots of other great webinars on other topics like functional safety and cybersecurity. So on that note, I will again say thank you for joining and have a good rest of the day.